Okay, maybe we can gently get going. There are still a few people joining, but I will get this show on the road and then we'll introduce our speaker. So this is Denise Kabuzda at University College Cork in Ireland. I'm very happy to welcome you on behalf of the organizing committee to this latest in a series of seminars sponsored by the European VLBI network, focusing on high resolution radio astronomy. Let me mention just a few logistics of the webinar before we begin. You will be muted throughout the presentation, but you're invited to type in any questions you may have for our speaker through the question and answer facility. You can send in questions both during and after the presentation, but questions will be answered only after the presentation. Please try to write your questions clearly and keep them short, and we'll aim to get to as many of your questions as we can. We apologize in advance if your question is not among those we have time to answer. Okay, and now I'll turn things over to Benito Marcote, who will introduce today's speaker, Pikky Atri.
Thanks. I have the pleasure to introduce Pikky Atri. She is currently a postdoc working at ASTRON in Bungelo, the Netherlands, where she has moved basically after getting her PhD in physics that she made in the Curtin University, UNICRAR, in Perth, Australia. And during these years, Pikky's research interests have been focused on studying compact galactic binary systems, in particular those ones that host a black hole. By studying these systems with very high resolution radio observations, Pikky has been able to constrain the jet emission and also the proper motions of these systems that help to understand the natal peaks that these systems suffer and also how the jets are launched. So this is basically what Pikky is going to talk to us in the seminar, and then I will just leave the floor to her and do the seminar.
Thanks for the introduction, Benito. I'm going to start sharing my screen now. Can you see the normal view?
No, we don't see the sharing now.
Yeah, we don't see your screen yet.
Okay, wait, I'll try again.
Yeah.
Yeah, that's better.
All right, the title screen?
Yes, perfect.
Amazing, okay. All right, I'll start then. Thanks, Benito, for the introduction. I'm Pikky. This is my first live web seminar. I've tried to make it as less dead boring as possible, so bear with me. Today I'm going to talk about X-ray binaries, focusing on black hole X-ray binaries in our galaxy. And I'll talk about how high resolution radio imaging and astrometry is actually progressing and pushing the boundaries of what we know about these systems. Before I dive into, before I dive into exactly how VLBI and high resolution imaging is helping X-ray binaries, let me just introduce black hole X-ray binaries to you. Black hole X-ray binaries are a system of a black hole with a stellar mass star. In this particular animation, it's a star of less than 1 solar masses. These systems, the star has matter which is flowing into the black hole, and this matter actually forms an accretion disk to conserve angular momentum. Now, sometimes there are instabilities in this accretion disk, which results in a huge dump of matter onto the black hole. This results in something called as an outburst event, wherein we see the black hole and the system, this binary system, get really bright across the wavelength bands. We know of 70 such systems in our galaxy, and we see around 2 to 3 outbursts per year across the sky. Now, these could be outbursts of new systems or of systems that already had an outburst some time ago. One such system called V404 Cygni, as you can see in this particular plot, as compared to Crab, it goes really bright when it actually went into an outburst. This is an integral X-ray light curve, so one of the X-ray satellites that we have. This black hole actually went into outburst after staying dormant for around 26 years. ESA preferred to call it the monster black hole. I would rather call it the zombie because it's not dangerous, just came back from the dead. So as you can see, this basically tells us stuff about the black hole and how the black hole is accreting matter, all of these black hole extrabinary systems. Now, these systems actually give us a really good view into how black holes are born and how they evolve, which then ties directly into the gravitational wave observations that we keep getting nowadays. And as you can see, most of the progenitors of the gravitational wave events lie in the stellar mass black hole range, so within 5 to less than 100 solar masses. So of course, if we study black hole X-ray binaries, which are more accessible within our galaxy, we'll be able to understand how these systems form and evolve at a more black hole binary level as well. Other than giving us a view directly into stellar mass black holes and their progeny and their evolution, these systems are also almost like small scale AGN, small scale supermassive black holes. So on the left, you can see a panel, which is a M87, which got really popular with the EHT image. It's a high resolution image of that. And on the right side, you see a Cygnus X1, which is a galactic black hole X-ray binary source. Now, as you can see, because Cygnus X1 is galactic, we can actually see it on a larger scale as compared to M87, because of course, first of all, the masses are also different. And also we have Cygnus X1, which is closer to us. Now, the jets from these radio systems can be, of course, maybe better studied with galactic systems. But if you want to study things which are closer to the gravitational radius of the black hole, then we, of course, need more massive systems, because the less massive systems are going to have very tiny gravitational radius. And so for those systems, we prefer studying AGN directly. But otherwise, black hole X-ray binaries seem like they are a very nice gateway to understand even AGN. And of course, this only works if you have a direct mass scale relation between galactic microquasars and supermassive black holes, AGN. In terms of how the jets from these systems vary, on the left panel, you can see a quasar, and you can see going from 1992 to 1995, the red things are basically jet blobs coming out of these systems. The jet blobs varied around 5 milliarc seconds in a span of 3 years. Whereas on this right panel, you see a microquasar, so a galactic black hole X-ray binary system, which had a movement of the radio blobs of 800 milliarc seconds over a week or a span of just 5 weeks. So clearly, if we want to observe and study these systems, the evolution of the jets and the structure on human timescales, it is slightly easier to follow microquasars and galactic black hole X-ray binary systems. Of course, when we study these systems, the movement of these jets, what actually we're getting out is the speed of the ejector. And that directly ties into how these jets are launched, what are the energetics of these jets, and also what the environment of these jets are. So, of course, I'll be focusing in this talk on radio jets from microquasars or black hole X-ray binaries. And these black hole X-ray binary jets are actually usually seen in 3 different states. The animation that you see moving now is a hard state jet. So the radio jets are causally connected to the black hole system itself. And the accretion disk is slightly further away. Now the second animation that you see moving, wait a second. Yep. So the second animation that you see moving now is where the jets get launched from the black hole and are seen as discrete ejecta. And so they are no longer causally connected to the black hole. In this case, the accretion disk has moved very close further to the black hole. The third state is a soft state where no jets are observed, and we just see very high soft X-ray emission coming from the accretion disk itself. Now, if this were a live audience talk, I'd ask you if, in case one is supposed to measure where a black hole is using radio jets. So you track radio jets and you see where they are, which state would you prefer? That would be the one in which the jets are causally connected to the black hole. So that would be the hard state jets, the leftmost. Whereas you want to see how jets are evolved and launched, one would expect to see more such stuff in discrete jets. So using these radio jets, I'm going to focus on mainly 2 things, astrometry and imaging. For astrometry, I'm going to talk about how black holes are born. So on the animation that you see a yellow track, which is basically the sun going around in our galaxy, and the orange track, which is a black hole X-ray binary system, and the track that is following in our galaxy. So clearly there is something different happening with the black hole system because it is not following the natural motion of the rest of the stars in the galaxy. Now, in order to know what is happening there, we need to find out what the proper motion is, how the system is moving. We get to measure the parallax of the system. And we should also be able to measure the orbital parameters of the system. And thus, that will tell us something about, I'm sorry if you can hear some background noise. That will also tell us how the black hole was born. The second bit is the radio imaging, in which you see how the jets are getting launched, which is directly tied into how much matter is getting accreted onto the black hole. And so that tells us how the jets are formed, what the connection to accretion is, and what the jet launching mechanisms are. In order to follow the radio jets, we need to have some radio observations, and the kind of telescopes that we use are called radio interferometers. Now, in terms of what they are, so in order to measure the proper motion of these systems, say a few milliarcseconds a year, we need really high resolution, 10 to the power minus 7 degrees a year. And resolution is inversely proportional to how big a disk or how big a radio dish you can make. So if you want some mid-level resolution, things like the VLA, which is like a Y-shaped antenna would work, or E-Merlin, which is dishes within England, that would work. But if you want really even further higher resolution, what do? You need, for example, resolution as big as the surface of the Earth. You really can't be going around making dishes as big as the Earth. So the next step is something that nice analogy that I heard in the EHT documentary on Netflix the other day, is basically imagine you have this huge piece of glass and you've broken it into shards and spread it all across the Earth. And you're looking at the same thing with all the shards combined at the same time. So basically you get pieces of what you're looking at, and then you try and get a complete image using those tiny images that you've gotten. And that is what very long baseline interferometry does. In this particular talk, and because I've just used 3 interferometry arrays across the globe, the first one is the very long baseline array, so telescopes spread across the US subcontinent. Then the European VLBI network, so there are dishes spread across Europe, China, there's one dish in Africa, and there are more up-and-coming dishes and joining this network soon. And the long baseline array, so mostly dishes spread across Australia, Africa, and one in New Zealand as well. So using all of these dishes, we then move on to how we can understand radio jets. So the first thing I'll talk about is how imaging is helping us understand how black holes evolve. So basically tracking the motion of the jets of these black hole X-ray binary systems. I'm going to use the example of GRS 1915 plus 105, which is a black hole X-ray binary system, which was first observed with the VLA by Mirabel et al. In 1994. As you can see, the jet blobs, depending on the week, were slowly moving away from the main core. In the next panel, you see a more zoomed in version of just the core, which was seen with the VLA, now with Merlin. So we've got we've got longer baselines, which means we have better resolutions. We see these blobs moving away, even with a more higher accuracy. So what is happening here is, once you see the blobs moving away with higher accuracy, you're able to see when exactly these blobs were launched. So you get the time of the launch of these blobs, and you get the zero separation. Once you get the zero separation, you're able to calculate back what the speed of these blobs are, and then ultimately speed of the blobs, which then give us information about the surroundings, about the jet launching mechanism, and also about how broad the opening angle of these jets are. So if you have the 2 blobs, so one is the receding and one is approaching, the 2 different blobs that are coming out of the black hole system, you have the proper you can measure the proper motion of these, and then if you know the inclination angle of these jets, you can directly get the velocity of these jets as compared to the speed of light. So for this particular black hole system, as you can see, the jets were really highly relativistic. In order to actually find if they were absolutely 1C or not, we just need basically better velocity resolutions. And that can only happen if we have better understanding and more accuracy of the measurements of time and measurements of proper motions. The other thing that we can do with just imaging these radio blobs is measure if these jets precess. So V404 Sydney, the zombie black hole that I had mentioned a few slides back, that went into a very, very bright outburst. And so with VLBA observations of a single 4-hour observation, it was seen that it is ejecting some blobs, as you can see in the animation that's doing rounds now. Now, these blobs in every 2-minute snapshot seem to be changing position angle, as can be seen in the bottom panel. So every blob that was seen seemed to have a different position angle. Now, based on the change in this position angle and how these blobs and how bright these blobs were, the authors could actually come up with some models on what was happening in this black hole system during this extremely bright outburst phase. The issue, of course, was that the system could not be tracked after a certain time because the blobs had become very, very faint. But until then, the blobs could be traced. And this was the model that was suggested for these blobs. So the black hole is actually, the jet is actually precessing, and the discrete jet ejection that I had mentioned earlier is then thus not just in a straight line along the jet axis, but actually precessing as well. So this very accurate observation then gives us insight into the fact that these precession things can happen during a particular phase in the outburst. After this, now I'll start talking about how astrometry, or getting the positions of these sources, helps in understanding how black holes are born. So as I mentioned earlier, I'll be talking about proper motion measurements and parallax measurements and how that ties up in our understanding of black hole birth. For stellar mass black holes, we know that they are born when a massive star dies, but exactly how this death happens is still not very clear. There's two mechanisms that have been suggested. The first is with a supernova explosion. So a massive star runs out of fuel, throws away all this stuff in a supernova explosion and dies, which gives a tiny proto-neutron star. Because of more fallback matter onto the proto-neutron star, you're left behind with the black hole. So you have a huge supernova explosion and you get a black hole. The second suggested mechanism is actually called a direct collapse. So there is a massive star, runs out of fuel, but instead of going off in a huge, very bright supernova explosion, it just seems to vanish from sight. Now, this is a HST observation. And as you can see, there was no trace of anything happening visibly. It's just that the star has vanished. And one of the leading explanations for this kind of thing is that it's actually probably a direct collapse star and it just formed a black hole. And so, of course, now we have these two mechanisms. The issue is we see these black holes after they are born in the current epoch, right? There is no way for us, how do you go from seeing these sources now to knowing how they were born? So you need to have some way of tracking the current situation of the black hole system to when it was born. So there's a birth property that we can study. It's called the natal kicks, in order to associate the current way the black hole systems are to how they were born. Now, natal kicks is something that a compact object receives when a system goes off in a supernova explosion. So as you can see in this particular animation, there's a binary system of two stars. One star goes off in a supernova explosion. Now, what this does is moves the center of mass of the whole system. And this sudden shift of center of mass of the system gives a recoil velocity to the rest of the system of the order of a few kilometers per second. So the system is then seen moving around the galaxy with slightly higher velocities. Now, if there were additional asymmetries associated with this explosion, you would actually see the system going around the galaxy with really high velocities. Whereas if you don't have such amount of mass which was thrown away, which means the black hole was born with a direct collapse, you will not see the system move around with such velocities because it does not get a recoil kick or even have any asymmetries in the supernova explosion. So one way in which to differentiate between the two, the direct collapse and supernova explosion, is just to see how the system is doing now, how it's moving today in the galaxy, and be able to say then if it was born with a supernova explosion or with a direct collapse. Other than telling us about the difference in the two birth pathways of a particular stellar mass black hole, natal kicks are also very important because they tell us if there's actually a relation between how massive a progenitor is and which method it chooses to become a black hole. Of course, depending on how the black hole is born, with or without supernova explosion, it then further affects how the stellar system, the binary system, evolves. Depending on how strong the kick is, one might end up unbinding a binary completely, which then reduces the chances of the system becoming a black hole binary in the future, which then reduces the chances of black holes actually merging to give us gravitational wave events. As you can see in this plot, an increase in sigma, which is the kick velocity, actually decreases the rate of events that we expect per year. So natal kicks, important thing to study about black holes. How do you measure these things? Well, you have current space velocity. You measure the space velocity of the system in the current epoch, but you have to find out the velocity that the system was born. So you have to make a time machine, go back in time, and find out the velocity of the system at birth, which is the natal kicks. But the issue is we do not really know the ages of these systems really well to go back in time to the age of birth. So instead of that, what we do is measure the velocity of the system every time it crosses the galactic plane. That is because we assume that most of these systems are born in the galactic plane due to high galactic plane densities. As you can see in this particular animation, again, this system goes through the galactic plane, and what we do is then measure the velocity every time it crosses the galactic plane, which gives us a velocity distribution, which we use as a probe to say that it's the natal velocity distribution of the system. To measure the current space velocity of the system, we need three important parameters: proper motion, so the velocity of system in the plane of the sky, the radial velocity, the velocity of the system towards or away from us, and of course the distance to the source. If you combine these three parameters, you basically get the 3D motion of a black hole, of any system. So for proper motion and distance measurements, we require radio observations, and that is what I'm going to be focusing on in the next few slides. So for proper motion and parallax measurements, I'll take the example of maxij 1820, which was a source that went into outburst a couple of years ago. And we could track this source with VLBA and EVN. And as you can see, we tracked this source over a course of 8 epochs. So this source stayed bright for a while, died down, and then had a couple of more mini flares, which allowed us to track the motion of the radio jets throughout this whole outburst. Now, what this has allowed us to do is not only, if you can see the plot, the top is the RA offset, the bottom is the deck offset in the plane of the sky. So, and we have the position measurements spanning number of days. So we can, with more number of observations, we can not only fix the motion in the plane of the sky just in a straight line, but also have the parallax fitting to the source. So after we remove the proper motion of the source, which will just be a straight line, then you can see some extra wiggles, which probably is the parallax of the source, which is on the right side. So using a combination of VLBA and EVN, we could get really precise parallax measurement for this particular source, which gave us a distance of around 2.96 plus minus 0.3 kiloparsec. Again, very high accuracy thanks to the VLBI observation we had with 2 arrays. Now, having the distance of the source and the proper motion, we've already tackled 2 of the main 3 things we need to measure kick velocity. The third thing is the line of sight velocity, on which we rely on optical spectroscopy. We got that measurements from our collaborators. Combining these 3, we measured the velocity of the source every time it went to the galactic plane, and came up with this plot of potential kick velocity distributions. As you can see, the median of the distribution lies at around 120 kilometers per second. To put that into perspective, the rest of the heaviest stars in the galaxy have a dispersion of around 50 kilometers per second as they move around the galaxy. So 120 kilometers per second is really high as compared to that. And so we suggested that this source was probably born, the black hole in the source in the system is probably born with the supernova explosion. This is just one system. We had archival as well as some new observations for 16 other sources. So for all 16 of these sources, we could conduct the potential kick distribution analysis, and we came up with kick velocities of these 16 sources. The good part about these distributions is the fact that even if the proper motion errors and distances are large, we can still get some constraints because we're using Monte Carlo simulations. So we just include those error bars in our simulations. So as you can see, a few systems still have some loose constraints, which can be improved if we have better measurements, basically. 75% of these 16 sources were actually seen to be born with supernova explosion. So really high kick velocity distribution. Now, that just tells us that maybe majority of the systems in our galaxy prefer to be born with supernova explosion. We use these 16 systems to say something about the potential population kick of these sources. Now, the top panel and the bottom panel are 2 different fits that we tried to do for the combined distribution of all 16 sources, the unimodal and the bimodal fitting. The unimodal fitting gave us 167 kilometers per hour median, which is again a high median. And the bimodal is somewhere close to 40 kilometers per second and 130 kilometers per second. If neutron stars are something that are familiar to you, this bimodal distribution is actually 3 to 4 times smaller as compared to the bimodal distribution of the kicks in neutron stars. So which then shows that maybe, and if one recalls, the mass scaling between neutron stars and black holes is also of the order of 3 to 4. And so maybe this could just be an effect of the mass scaling between black holes and neutron stars, that you see black holes move with smaller velocities as compared to neutron stars. As I had mentioned earlier, we also try and see if these velocities are actually connected to the mass of these black holes. This is a plot which tries to see if there's a relation between the kick velocity and black hole mass. In this particular sample set of 16 sources, we actually could not see any correlation. So it does not necessarily mean that a heavier system has to be born with a smaller velocity. But as you can also see in this plot, the error bars on the masses of a few systems are quite large, and a few of them are also centered on the 8 solar masses, which was actually the assumed system of mass of the system. And so the way to improve this is going to be, first of all, make these error bars smaller to get better measurements. And the second step would be to populate this graph even more so that we can try and get towards lower black hole masses and see how their kicks vary, and also higher black hole masses to see how their kicks vary. We also tried to see if there was a correlation between how high from the galactic plane these sources are found today as compared to their kick velocities. There was a slight possible correlation seen, but there are a few clear outliers. If you can see the GS1354 source and the VLA J2130 source, also the GRO 1655 source. Now, of course, 2 of these systems have quite large error bars, so we don't need to just get scared just now. But GRO J1655 has a good explanation for being such an outlier, is the fact that it was actually, if you see the motion of the system in the galactic plane, in the current epoch, it's moving towards the galactic plane. So it is likely that the system has gone to its maximum height above the galactic plane and is just moving towards the galactic plane now. Another way in which VLBI observations have really helped understand black hole parameters was this recent study and recent result on Cygnus X1. Now, originally we had just the parallax of this source was measured with 4 to 5 epochs. And as I had shown earlier, they could solve with the wiggly signature of parallax and then get a distance. After getting the distance, you find out what the absolute magnitude of the system and the black hole is, and then you try and get estimates on the mass of the black hole. Now, the new results, which were published this year, they've been able to track the motion of the black hole, not just for 5, but actually at least 8 epochs. What that helped them to do is they found out that there was some scatter. If you see the plot on the left side, the jet axis is the white arrow pointing towards upwards. There was some scatter in the radio emission along the jet axis. Now, what that entails is that there will be no scatter in positions perpendicular to the jet axis if the jet axis is the only reason we are finding the scatter. So they were able to fit for the motion in the for the motion of the radio emission perpendicular to the jet axis and get a better improvement on the parallax measurement, which then resulted in a better improvement on the distance of the source and hence an updated mass. Now, this mass is around 21 solar masses, which has, of course, many implications, but the most important one that I would like to highlight now is the fact that because it was such a high mass, it does not really fit into the current evolutionary models we had for these systems. So we've been forced to now rethink about what this could actually mean when it comes to evolutionary models for all systems. So again, a very good results thanks to VLBI. After having done some specific source studies, VLBI can also be used to actually look for some of these new sources. As I had mentioned earlier, most of these systems are seen when they go into an outburst. So when they go into an outburst, the X-ray satellites, they pick up some X-ray activity in the sky, and then the rest of the telescopes, we try and focus it on the particular source. What if, instead of using X-ray to detect these systems, we actually find out some way in which we can use radio observations to directly observe these sources without these sources having to go in an outburst. This actually then helps us to not get an observational bias. So we'll not be only observing systems which are suited only for outbursts, but also without outbursts, we'll be able to get some other kind of systems in our sample set of the study. So for such a study, radio surveys, so radio surveys which basically depend on radio variability studies, are a treasure, because they are able to see transients which might be known, and also in some cases which might be unknown and exotic. Becker et al. In 2020 did such a study where they combined 3 different years of VLA study over a timeline of 15 years, and they were able to catch at least 39 flat spectrum, highly variable sources. Now, based on the positioning and the location of these sources, as you can see in the plot on the right, the blue blobs, they are the flat spectrum sources, and they could be seen concentrated within the galactic plane, which forced them to think that maybe this sample is actually controlled, or it's more populated in our galaxy itself, in the galactic plane. Now, the next step to see what these sources actually are, because they could rule out a few possible categories of what these sources are, but they could not exactly tell what the nature of these sources are. So the next step would be to actually confirm whether these flat spectrum sources are galactic or not. And a very straightforward technique to do that would be able to measure the proper motion of these sources. As basic physics, if you see if a source is close to us and we see it, if you see a source moving and we see a source not moving, one option could be that the fact that the source is closer to us looks like it's moving, and the source that does not look like moving. So if you measure the proper motion, extragalactic sources, or sources which are not in the galaxy, will seem to be stationary as compared to the International Celestial Reference Frame, whereas galactic sources will be seen to move with some proper motion. So in order to do that, to study that, we actually conducted a VLBA survey of these 33 of the highest variable sources. And we could confirm that at least 6 of these sources are potentially new galactic black hole X-ray binary candidates. Of course, this is based just on preliminary proper motion measurements. We will need more optical and probably X-ray observations to confirm whether these actually are black hole X-ray binary sources. But this VLBA study, this kind of a survey is a great way to start to recognize any new exotic transients we might have in our galaxy. I would also like to point out that this VLBA survey was a filler time survey. So instead of blocking out huge portions of the scheduling time, we basically just asked for 1 hour blocks. And in that 1 hour blocks, we just focused on observing 2 targets at a time for half an hour each, which then enabled us to observe multiple targets of the order of 33 for multiple epochs, around 100 data sets, and then allowed us to measure proper motion, although with low accuracy, but that can be fixed later with additional further follow-up epochs. Now, this work is currently in publication. Not in publication. So I would like to leave you with this summary. As I've shown with multiple examples, it looks like VLBI is a key to unlock a lot of black hole X-ray binary mysteries. And this dives into not only the gravitational wave merger events that we see and all are so excited about, but also AGN studies. Of course, VLBI is playing an important role in measuring the proper motion and parallaxes of the system. And other than just telling us about the distance, these also tell us about jet launching mechanism system of these systems, tell us about the masses of this system, and also gives us ways to think about how stellar evolution is actually happening. Also, using proper motion parallax measurements, we've been measuring black hole stellar mass nickel kicks, and we see that 5% of the systems actually obtain really strong nickel kicks and are probably born with a supernova explosion. We are now in future works trying to look into ways in which we can keep on extending our sample set from more than 16, because clearly there are way more systems hiding in our galaxy, like we saw in our VLBA survey, which need not only be seen in X-ray outbursts. So yeah, that's it. Thank you.
Thank you very much, Pikky, for that great talk. We've got some questions coming in. Mm-hmm. One says, thank you, it's excellent work. It's great to see that VLBI plays a major role in measuring black hole X-ray binary proper motions and parallaxes, and that it has broad implications. Okay, so couple of questions. Why are Gaia parallaxes so rare? Is it because of absorption in the galactic plane?
So, I'm sorry, Gaia parallaxes so rare.
That's the question. That's what this
yeah. So the reason is there are multiple reasons. First of all, as I mentioned, most of these systems are only observed in outburst. And so the time period of when these systems get bright enough is not that large. And Gaia basically depends on scanning the sky. And so it's not necessary that we'll have an overlap between when this Gaia is observing that particular patch of sky and we have an outburst as well. Secondly, there is also most of these systems, because they are so in the galactic plane, there is a lot of extinction that might result in not that much optical wave or optical brightness that we might get. And so in terms of the proper motion and as well as parallaxes of these black hole X-ray binary sources, Gaia is doing okay, but not that great. So yeah, maybe in next Gaia epochs, with multiple rounds of the sky, we might be able to see something better. But that is why radio observations are really critical, especially such follow-up trigger ones.
Okay, thank you. Another question. Is scatter broadening a major issue for VLBI? And what would be your opinion about the frequency sweet spot for the type of observations you're talking about?
Yeah, so it is an issue. And so what we try and do is mostly observe in slightly higher frequencies. So maybe 8 gigahertz, or if not 8 gigahertz, then 5 gigahertz. Beyond, again, it depends on how bright the source is. So most of our targets were flat spectrum. So we were not really worried about detecting them in lower frequencies and then losing the flux in higher frequencies. For compact steep spectrum sources, that might be an issue. So for angular broadening problems, we usually just stick to 5 or 8 gigahertz observations.
Okay, thank you. Another person's question asks, in the zombie black hole, so you've obviously done your bit to give it its name. In the zombie black hole, could the precession of the jet have been seen in the outburst 26 years earlier, given the space resolution at the time? Do we expect the precession to be the same?
For that, so the reason we saw this particular precession in the current outburst was because the outburst was really bright and the accretion disk actually ended up dragging the space around the black hole, and thus giving the jets those precession. Now, 26 years ago, I'm not really sure if the outburst was this bright. So it has a lot to do with how much mass accretion was happening and the luminosity of the system. So I'm not sure if we would have seen the precision. And also, I'm not really sure if we had such good trigger observations with using VLBA 26 years ago. I might be horribly wrong, but yeah, I'll have to go back in history and check. Yeah.
Yeah, I think you might be right about that. That's something that's really been developing a lot lately.
Yeah.
Okay, a couple of people have asked on the same question. The EVN data points have larger errors on the larger errors than the VLBA data and the parallax measurement of maxij 1820 plus 070.
Yeah.
And it was noted as being a kind of an obvious outlier. Do you know the reason for this?
No, that's the honest answer. I do not know. And trust me, there was a lot of work that went into trying to figure out why this was an outlier. One of the reasons I could see was because we had more VLBA epochs. We used that as a reference source to correct. So there were calibration issues. Both the set of observations have had different calibrators. So we had to shift for any possible core shift due to different calibrators, use of different calibrators. And because we had more VLBA epochs, we used that as a frame of reference. Also, there were 2 different frequencies. So it was not just 8 gigahertz, it was 8 and 5 gigahertz. And so there could also be some shift in the frequencies, again, because we had specifically designed simultaneous VLBA observation to get that frequency shift. We use that as the base to correct EVN epochs. So it could be some combination of that I see happening, but exactly what the reason is, I'm sorry, I won't be able to tell you.
Okay, another question's come in. Do you know if natal kicks, besides their influence on merger rates, also have a measurable influence in the resulting gravitational wave signal?
Oof. It could, yeah. So again, natal kicks if they don't unbind the system, they absolutely do affect how the system evolves in the future. So if the kicks are strong enough and in a favorable direction that you've just ended up extending the size of the binary, the time of the merger, of course, is going to increase because it'll take more time for the system to get nearby and merge. So it might just not even happen. In terms of quality of merger, I don't know of a particular direct connection, but the only thing I can see is it might increase the time needed for the merger to happen.
Okay.
Or decrease if the kicks push them in the other way. Yeah.
Yeah, thank you. Another question. You showed an image by Sterling et al. From 2001, which is quite a while ago now, of SIG-X1.
Yeah.
It was very striking because it really looked like a Corjet AGN, even though it was a stellar system.
Yeah.
And,
yeah.
Is this typical, or is this a bit unusual? Are there better images that have come along since then, or?
Yep. So if you see this image now, on the right side, this is a 2021 image. It's a stacked image of around 8 VLBA epochs. So it does look like a double core jet system. Now, the reasons could be, first of all, that we are basically stacking the scatter along the jet axis. And also, this is a high mass X-ray binary system. So there could be some influence of winds, because in high mass X-ray binary system, it's not just the Roche lobe overflow that results in accretion and hence the jet. It's also some sort of wind accretion that might happen. So that might also influence the way we see these systems. Cygnus X1, because it's quite nearby, is actually one of the special sources in which we see this elongated sort of double lobe structure. But I think it's highly because of the scatter along the jet axis that now we know of, but originally we did not. Okay, so is the jet here intrinsically one-sided or two-sided? It is two-sided. So if you see on the left side, the points on the top along the jet axis and at the bottom. So those are two different axes. And the circle that you see is actually the orbit of the black hole around the center of mass, which is given by the star. And so the jet axis is like that. And that's why, since the source is going around, the scatter is along different directions. The dashed lines are where you would expect the points to be if there was no scatter along the jet axis. Okay, thank you. And another question concerning the direct collapse black holes. Mm-hmm. How is it possible to test for the presence of the black hole corresponding to the star that has disappeared? Mm-hmm. And do you require a binary to get a direct collapse black hole, or could this happen with a single star? Oh, it could happen with single stars as well. Yeah, I think this particular case. So to answer the first question, in order to see if there's a direct collapse black hole, it would be very convenient if the system was actually in a binary, and we see a binary, just a star moving around or going in an orbit in something which we cannot see. And we also saw that the star just vanished. So it will be one of those observations which are just a discovery observation that you get really lucky of observing multiple things at the same time. The second question was, no, this is just, if a star is massive enough and it leaves behind a proto-neutron star that, like the star is just massive enough, or so is the current theoretical models, that it just does not allow any stuff to go away or throw out, and all the stuff just goes right back into the core that was collapsing, you will see a direct collapse. So it does not necessarily have to be in a binary. Similarly, with the supernova explosion mechanism as well, it does not have to be in a binary. It's just that the follow-up kick scenarios do get aggravated if the systems are in a binary. Okay, thank you. Do we have any more questions? I don't have any in the question and answer at the moment. Benito, do we have any from YouTube?
No, those are all.
Okay, maybe we can wrap things up. So thank you very much indeed, Pikky, for a very interesting and followable talk for somebody who doesn't work with black hole X-ray binary systems. Thank you very much indeed. And also we'd like to point out our next seminar coming up. You'll see it on your screen now. Ivan Martí Vidal is going to talk to us about tying the sky to the ground on Friday, 9th of July at 1500 Central European summertime. Thanks very much, everybody.